Hello everyone. This video is mainly about how to work out through this problem. The objective that we are doing here is handling images or processing of enhancing images using CNNs. The main thing that we are focusing here on this in this practical on this video is mainly thinking outside the box, outside the norm of having a pre-trained neural network. You feed it few images and you can demonstrate how good it is. Now we are thinking about what the problem is and how to formulate it, and working around the several constraints that you would face when thinking about these kind of problems. There are two tasks. As I said in the tutorial, I will not be doing task one. This is fairly straightforward. You already have done that before with the MNIST dataset. The only difference here would be for you to choose some classes, download few images, of course, 20 or 10 images, very, very low number, and your network is likely to overfit, but you can compensate for that by doing a very, very small neural network. It can work, but you will eventually need more images. But this is just for demonstration purposes for you to just get your hand to things working. You will be doing two models here. One of them is just classifying into one of the predefined classes. And please just don't bother trying to run this on GPU. You will waste your time for now. Keras and TensorFlow. For GPU, you will need certain version of CUDA and things like that. So just uh, maybe use a reshape layer or something to or a resize layer to make the images into a reasonable size, like 28 by 28, similar to MNIST, and then you can just run it on CPU for now. The second model would be, again, you can still reshape images and so on. The second one would be doing an autoencoder to learn some features and then isolate the encoder and then attach a dense classifier to it, train the model, and then see how fast it would train for you. The second task is the one that we discussed in the tutorial, and the idea here was to de-blur images or enhancing images that are blurry, given using a CNN, a convolutional neural network. And the example that we are showing here is we have a filtered or a blurred image, and we want to de-blur it to its original self. Obviously, it's not really that straightforward to actually reach the original self. You might need to clean up some of the noise in the background, but this is what we are going to do. The data we are working on is the MS dataset, and the input is a filtered or blurred image with unknown parameters, and the output would be unfiltered blurred images. Notice here I said module, not model, and the main reason for that is that you can either, as we discussed in the tutorial, you can make a model that can do this end to end, but you might also need to make it generic enough for the model to instead of this, estimate the unknown parameters instead of the image itself. With that, we discussed few ideas, and one of them was to use autoencoder, in which you would feed pairs of images and the blurred images and the blurred original images to the autoencoder, and your CNN should learn how to map between these two. The other idea that was also discussed in the tutorial was to use regression CNN. So we need CNN or CNN layers to learn the features and a dense layer to learn the parameters. And the regression CNN here, it was to learn filter values. And this is actually a very good idea. The main idea is that if we have a way, say, if I have an image I and I will do a convolution with a filter F, it should give me, say, I hat, and this would be the blurred one. Now, if I have I hat and I have some operator, let's call this some deconv operator, and I can do this deconvolution with I hat, it should give me I, which is the original. So in this particular case, we want this CNN plus dense layers to regress or to estimate the parameters in F. For example, in for blurring an image, F could be 1, 1, 1, 1, 1, 1, 1, 1, 1, and I think there is a, oh yeah, okay. And all of this should be divided by 9. Now, if we can estimate what the F is, then we can, and we do have a deconvolutional operator, then we can do that. A third idea was, and this was discussed briefly in the tutorial, we haven't gone into the details, is to use similar approach here. So we need the filter parameters at this time, and we see that we estimate to learn the features and dense layers to learn the parameters. Um, yes, and we will go, in this time, we will be using more generic type of filter. So the idea in the second one here was that we will estimate this 1 over 9, 1 over 9, 1 over 9, and so on, and let the machine actually deal with it. The drawback of this one is we are fixed with the filter size. Now, in practical use, you might do some survey and find, say, yes, the majority of blurring would happen between filter sizes, say, 3 and 9, and then you can maybe train 3 different models for that. If you're working on papers, you usually want to, or academically, you usually want better like approximation or a more generic formulation of the problem. So instead of using average filter, we can use Gaussian filter. Now, with the Gaussian filter, we need to specify the size, and we need to and the sigma. Let me show you how, what I mean by that. I'll just borrow one of the things I had here. Where did that go? Yep, let's take this one and let's do it here. By the way, I'm doing this live, so I want you to experience all the mistakes, the debugging, and so on. So we will laugh, cry, and we will have lots of fun. Now, let's try this one. Gaussian. Oh, no, I need to run this entire thing first. Okay. Tick, tick, tick. Gaussian filter, and it takes shape 5 and 5 and say sigma 1. So if we just do this one, it will show you these numbers here, and usually it will give you or it is designed to give you the highest value here, and it always sums up to 1. So if we do this dot sum, should give us 1. Now what happens if we do the sigma equals zero point 0.1? You see, it will give you 1 at the middle and then zeros everywhere. So we can start with a fairly large filter, and then this sigma would allow us to control how the filter is shaped out, um, depending on the number of or the level of blurriness. To give it in perspective, let's put this as 5. It's a fairly high number, and this would be almost like an average filter. All right. So this is what we're trying to do here. Now let's confirm that this would be similar to an average filter. This still sums to 1. Actually, it might have some truncations somewhere. Okay, so what we want is to deduce what the sigma is. Only need to deduce what the sigma was. Then we can reconstruct a filter with the same sigma and the predefined size and use it to deblur the image. Fair enough. That is cool. Okay, now that we have demonstrated what the Gaussian filter can do, by the way, this function is kind of an implementation of a function in MATLAB called xSpecial, which can generate these filters for you. It's not available in NumPy or SciPy, so I grabbed this function from Stack Overflow, I believe, yes. Now, the other piece of the puzzle that we need is the deconvolutional operator, and this is one of the beautiful things that you will see with Fourier transform. Now let's add here deconv operator. Now, if I have a function f of x and I'll pass it through a Fourier transform, it will give me f capital of x. This is the notation being used. Now, if I have another function f of g of x, and we'll pass it through Fourier transform, will give me G sub X like this. All right, now if I do F, this is one of the properties of Fourier transform. F of X convoluted G of X and pass this to Fourier transform. This will give me capital F of X times capital G of X. And that's one of the nice things about Fourier transform. And it goes the other way around. If you do F of X dot or multiplication by G of X, this will be capital F of X convoluted by G of X. Now, you can probably see where this is going because Fourier transform is reversible. So whatever we have, whatever we transform with the Fourier transform, we can reverse it with the inverse Fourier transform and go from capital F of X to capital G of X to F of X and so on, similar with the G. So how can we use this to our advantage? If I have an image, I'll call it IM of say X and Y, and we'll pass it. And now, because we know we can reverse that, this will give me capital IM of X and Y here. Now imagine I have a filter of X and Y. Let me just add some spaces there. This will give me the same filter, capital letters, X and Y. Everything on this side is the time domain or spatial domain, and everything on the other side is the spectrum or the frequency domain. Call this time slash spatial. It's called time domain if you're working with time series, and spatial domain if you're working with multidimensional, like images or 3D points and so on. And let me put this here. Everything on this side will be spectrum or frequency. Now let's just call it down. So this is a very nice property of Fourier transform, and the best thing is if I have an image in the Fourier space or in the frequency domain, and I have a filter in the frequency domain, if I divide the image by the filter, it will give me the image unfiltered. So this would be our deconvolution. So if I have a blurred image, let's say a blur of X and Y, all I need to do is to pass it through Fourier, and this will give me this one. Come on, right? Now, our filter is probably generated this way. This is what we're trying to do. So our machine learning model will try to estimate what the sigma is, right? And then we can generate this filter using this function, and then convert it to Fourier and do the deconvolution. Okay, so let's start doing that. Now let's see what functions do we have to do the Fourier transform. It was in SciPy library and the image. So I'll say and the image dot fft as it dot Gaussian. Oh yes, this will just filter the thing. I'm looking for the Fourier transform, which is supposedly somewhere here, maybe. Okay, so now FFT dot, we have several functions of Fourier transform. DCT is the discrete cosine transform, which is used in JPEG conversion. We have FFT. This is the first one-dimension Fourier transform. This would be helpful for your EEG work or any time series work. There is FFT2. This is the Fourier transform for images. So this will be your 2 dimensions. And there is also a generic one called FFTN, in which you would specify how many dimensions do you have here. Now you also have the inverse. So you have inverse BCT, inverse FFT, and inverse FFT2. Okay, so we can do FFT2, and we can pass whatever filter that we have here. Call it filter. And let's just print it to make sure it actually went through. And there you have it. This would be the Fourier transform of this filter. Now, few things I want you to notice here. These numbers are complex numbers. They are not real numbers. So they are composed of real part and an imaginary part. The imaginary part here is using the J terminology to justify the or to refer to the imaginary component. For the majority of the cases, you just can't get away with just getting the real part, but we want to keep things authentic, so we'll just leave it like that. Now we need to see what the image, how to do this for an image. So let's load an image. Where is the, I think it was here. How do I load an image? There it is. And then I can do fft.fft2 and give it the image. Probably I need to average this at axis equals 2. And just to make sure, let's check the shape first. Basically, I'm trying to avoid having a 3-dimensional Fourier transform here. So this would be a 2-dimensional one, which is nice. And this would be the spectrum of the new image. It should come out in the same shape. So if we print that shape and see that other shape should come out with the same shape. Now, if we want to filter our image, then we can, all you need to do is just multiply. We want to filter in the time or spatial domain, so we want to multiply the spectrum or the frequency domain components by each other, element-wise multiplication. So to do this, we need them to be, for starters, the same size. So let's take this and let's call this image F for frequency domain. And this would be our filter, is it? So we call it field F. Now we have field F and we have image F. Let's check the sizes here. Image F dot shape. There you go. We have 5 by 5 and we have 480 by 480. Obviously, this doesn't work. So we need this spectrum to be at the same size of this. And this is one of the good features of fast Fourier transform algorithm, that you can specify what size of filter that you are looking for. So we will let's just group this into uh, one cell here to make things easier. Okay, so we want this filter to be at the same size, and there is one parameter here that you can specify, which would give you the size. I think it is the S sequence of integers, or it should give you the shape. Okay, so this should be image f dot shape. Now, if, yeah, that's I wanted to actually do it live so we can see the mistakes I'm going to make. Now, if we trend these two are exactly the same size, which is beautiful. Now, let's do filtered image. Let's just call it filtered. And because we will do the filtering in the spectrum in the frequency domain, so now we can have filter f multiplied by image f, and this would result in two signals multiplied together in the frequency domain. So this would be filtered f. Right, so far so good, and this should give me the same shape. Beautiful. Now, if we check this one, it will look like another frequency domain signal. You have lots of things here and there. What we want is this multiplication reversed into the time and spatial domain. So we need to simulate the convolution by doing the multiplication of the frequency domain. So once you do the multiplication here, you inverse the transform to give you the F1, the F convoluted by G. So we need to inverse that. So we call it filtered equals, and this would be FFT dot inverse FFT2. And this would take, um, oh, there's an S here. You can specify the size as well. Okay. I didn't thought they would do it that way. It's better than the MATLAB's version. Either ways, filtered F. So this should give us the image filtered in the spectrum, in the frequency domain, and then inverse transformed into the spatial or the time domain. So now let's say what filtered has. Oh, we haven't run this. Something is not right. Filtered. Cool. So now it gives us the what looks like values for images, which is good. Pixel values on the real part. On the imaginary part, there are very, 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 very small values, so you can actually ignore these. So we will do filtered equals FFT. Oh, actually, numpy.real. So we'll get the real part only from the filtered. There. Now, if we do this one, it should give us pretty much an image. Let's show this image. So we will do figure and the axis equals R. We will have so many figures. So let's just do it this way. Plot dot add subplots. I always forget how to plot. Oh, subplots. Okay. Subplots. And we'll take one row, two columns, and we want axis sub 0 dot im show. This is image show, and we will show the filtered image. Oh, something went wrong. Axis name is not defined. This is because it's axis 1. We're still doing a mistake. Ah, it's because it's 1, 1, and this is subscripted some. Okay, let's just 1, 2, and let's see how it goes. So this would be our image here. Now, if we do, we actually want this to be in grayscale, so we'll do CMap equals gray. I believe gray was like that. Sweet. Now let's see this in comparison with the original image. So we'll do the image here, and we'll do the filtered here. Same one. There you go. So this would be the original image, and this would be the filtered one. Now, if we increase the size of the filter, where is our filter? What's the default size? 5 by 5. Now let's do this. Say, what's it called? Shape equals say 9 and 9. And let's print the filter after. So this would be our Gaussian filter 9 by 9. Notice that values are higher in the middle and they get lower as you go out. Now you can see this is really blurry there. Now we have an image, a filter, and something to plot with. Let's do deconvolution. The deconvolution, our part here, would be reversing this one. So basically, we want the image f, so we'll divide filtered f by filter f. Let's call this convolution, and let's call this deconvolution. So what we want is to just take this one, actually we want to do it from the start. So we'll take filtered and we'll pass this into fft.fft2. This will give me filtered f2. Let's give it another name. And we want another filter, which is filt2. So we will do another filter here, filt2 equals Gaussian, and shape was 9 and 9, and sigma was, what was the sigma? 5. 5. Now fill to F of field F2. This would be FFT dot I FFT2 of field 2. Now we have the filter, we have the filtered image. Now we need the original. So call it unfiltered. This will be unfiltered F, and this will be FFT dot R. Sorry. This would be, okay, we want, this is this times this, so we want this, which is this divided by this. Filtered F2 divided by filter F2. Now this should give us the original image in the spectrum domain. Just for a sanity check, let's see what shape this is. Something's IFFT. Sorry, this should be actually FFT. Yep, and this should be FFT. And let's do that. Sizes don't match. Sizes don't match because this should be filter. Is it S equals filter dot shape? Brilliant. Now the unfiltered image should be FFT dot inverse FFT2 of the unfiltered F. If we check the values here, these are pixel values, these are negligible, the imaginary part. So it should work out. And we need just to clear it up to just get the real part of this. Okay. NumPy.real unfiltered. Yes. So now let's do a plotting. So we'll take this. Actually, you know what? We can just make this 3 and we'll copy that, put it here. And this will be 2. Axis 1. Oh, yeah, I need to do this again. Now we have an extra axis to plot on. And now it should come back. This still looks blurry though. Something is not right here. Ah, I plotted the filtered, unfiltered. Yep, that's much better. So let me take you through how we did so far. We loaded an image, we put it in a frequency domain, we prepared a filter, whatever that is, we put it in another frequency domain, and we did just a print. To filter, we just multiply in the frequency domain, and this will do convolution spatial time domain. And then to get the image back from spectrum domain to spatial time domain, then we need to do the inverse Fourier transform. And inverse Fourier transform will give you give negligible imaginary numbers. So we can drop these in negligible imaginary components actually. Can drop the imaginary components. And then we just plot it. We prepare the plot with three subplots. This, and this actually, we need to add some titles here because now it's a little bit messy. So axis sub-zero dot set title. Call this source. And this would be one, we call this filtered. And last one is this one, called this unfiltered. And this will be two. Let's run them all again. Oops, we made a boo-boo. Ah, axis one, one, and one. And this should give us, yes, 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 beautiful, beautiful. I want to move these, underline them. How did I remove them before? Ah, okay, yes. Just Stack Overflow, how to remove axis text. Plot lib. Mm-hmm. Come on. Ah, probably asking the wrong questions. I did it somewhere before. No, there it is. And yeah, we can add it here. Axis 1, sub-zero. You have to do it again for the y-axis as well. Oh, this is ridiculous. Okay, so I hate doing copy and paste. So we'll define show image function. Give it image and maybe color map. And the title maybe. Title will be empty by default. Color map will be gray by default. And we need an axis. Okay, so we'll just do this function. I'm gonna use it later anyway. What we want is axis time show something. Okay. X dot time show image with a CMap, and X dot set title. and then X. What was the last one? Yeah. Let's do that here. We'll remove the x-axis and y-axis. Basically, what I'm trying to do here is just removing this nasty numbers. We don't really need them. And then we'll just return. Okay, we have our function. Now let's comment all of that. And just show image. Which one is the first one? Image. And title equals source. I think we need x sub 0. And then another one which would be showing filtered. And this would be 1. Just to keep things a little bit consistent or visually appealing, we can do that. Does that work? Fantastic. Okay, remove all of this. And we'll just copy one of these. And this is filtered. We'll remove this one and add this. This axis one sub 2, and this would be unfiltered. Wait, oh, sweet. All right, so now we have probably all the components we need to do this trick. Now all we need is the sigma. What was our sigma? If we have this, um, if we have this filter, where was that filter? If we have this filter, what kind of sigmas are we feeding there? And this is the part, the only part that now we need to learn in the neural network. So instead of doing autoencoder, which means you will do regression over, say, whatever sizes that we had in your images, in MNIST it will be 28 by 28. You can, the next step or the more efficient way would be to do regression over 9 values and restrict yourself to only filters of 9 of 3 by 3, or then train multiple models for other things. Or you can use a Gaussian filter, and the only thing you need to really regress here is the sigma. Sounds straightforward enough. We need a CNN, we feed it images, and a dense network at the very end that will do regression over a single value called sigma. That is it. All right, let's clean up a few things. I don't really like the idea that I have to go through this every time. So let's put them into a function. I made a function here that would do that. This would be, oh, let's remove that. And let's make another cell here. So this would be filter image, which does Fourier transform over the images, and then inverse Fourier transform over the same images, and so on. Actually, we need to do it. Yeah, we don't need that now. Yeah, one last thing that I forgot to mention is that Technically speaking, if you filter an image, the black parts would be negative. Technically, we crop these or cap these negative values to zero. And this is how you can actually get edges when you do edge detection filtering. So we will, I just want these to be consistent with each other. So we are going to test these two functions here, and we'll make a similar figure to that at the bottom, mainly just to test things and make sure that things are working out. So let's delete this one. Let's go here at the bottom, and we want to filter an image filter would be equal to image filter or filter images. Yeah. What is our function? It takes image and filter. And let's see what filter has. As you can see here, I dropped all the imaginary components of the complex numbers and just did all the and capped everything to zero. Anything that's negative was capped to zero. Now let's do unfiltered of this would be unfiltered image, which will take filtered and the same filter. And let's do unfiltered here. This is printing down, it always prints the last one, so this is printing the unfiltered part here. Now let's do a figure, which would be, where is our figure? Yep. And let's call this figure 2, axis 2, and we'll show image. Yep. Show image, and this will be source 0, axis 2. Filtered, this would be at 1, and this would be filtered, and this is unfiltered. This would be 2, and this would be unfiltered. Result of item. Yeah. Now let's make the, say, this filter much bigger. Okay. I want to plot the filter to, I want to print the filter, print filter. You can see there are many, many zeros because the filter is way too big for the sigma to cover everything. There's also another factor to consider. Very, very big filters will have to pad things with zeros at the sides. So it is not advisable to really use very large filters. But if we say stick to say 9 by 9, this should be good enough. Now, if we change this sigma to say zero point 0.1, as I showed before, it will give you 1, and then everything else would be zeros. So basically, it is not technically filtering anything. And the unfiltered will be also another copy of these two. If we do this at say 1 sigma, then it will be filtered a little bit, and the unfiltered will get it back easily. Okay, so now we have all the components we need. We have a function that can show images. We have a function that can filter images using Fourier transform, and another function that can unfilter an image using Fourier transform. Next step would be to prepare our data and then our model to do the regression over the only missing parameter that we need to do regression on, which is the sigma equals 5. Okay, so now we want to prepare our data. Let's make a new cell here, and let's take the what's called the MNIST dataset. Where is the datasets? How did I import that? Well, it should be there. Dot data. I actually cannot remember how I imported the datasets. So let's get it from one of the autoencoder maybe. Datasets. Yeah. TF.class dataset. Okay. So we'll do that here. Now we'll get the training x training y value validation x validation y. We want to generate samples of this dataset that are um, blurred, and we need to keep the sigma that we use to blur these images. So we will define a function prep dataset, and this will get say data, or let's call it images, and that's actually enough. In here we will do for image in images. What we want to do with that is image filtered equals filter image, and we'll give it this image. Now we take another thing here, which is the filter. So we need to define a filter equals Gaussian filter, and we will restrict the shape to S and S, and let's put S equals 5, here, and then what else? We want sigma equals sigma. Now let's get this sigma randomly generated. So we'll say sigma equals mp dot random dot rand. Okay, so if we go with rand n, which means it would be random, normally distributed, this means we have negatives and positives, and we also may have zero. It's highly unlikely to get zero, but then we might need to square them or get the absolute. Another way, and that's also with the normal distribution, most of the sigmas will be around the zero, so the data set will be biased. The other way would be to use rand, which is a uniformly distributed one, and it gives you values from 0 to 1. So again, it's highly unlikely to touch 0, but just in case, we'll just add an offset there, just in case. And then we need to scale this up to say, what is our maximum sigma? Let's say max sigma equals, say, 9. Offset sigma equals 0.01, and let's make offset sigma. Notice that everything I use, I try to like pass it as parameters in our function, and if you don't really need to change it, you just add the default value here, and then you can use it there. The reason I'm using it this way, or that the reason it is the best practice, is that by modifying just the input parameters, then you can get a consistent result for that. Now this would be image filter. Now we need to pack these into a new output. We'll take the same size or the same shape as training X. So out data equals images dot equals images dot copy, and we'll just multiply by 0 just to make sure that this data has been changed and it's not the same data that was copied. This is mainly for sanity check. You don't really need that, but if you like doing this on a project you just started on, it might be good to actually make sure that this is it's more like a sanity check for yourself. I think another way to do it is MP zeros like, and I think here you pass another array, which would be images. Probably this is the best way to do it, or a better, more efficient way to do it. Okay, so we have the, I don't like this name. And let's call this source image. Alrighty, so we have our filtered image. Now we need to add it to our data. So our data sub I, yes, we need to index that. So we'll have I and source image in enumerate the images, and our data sub I would equal filter image. Now we need to keep track of the y's, which would be the sigmas. And this would be an empty list and uh, np dot zeros uh, length of images. I believe this should be like that because zeros takes a tuple the start, which is the shape. Shape is an integer. I think it's if it is an integer, it will give you a square matrix. Why are we doing this thing? Let's just try that. np dot zeros 5. Oh, okay, cool. So we don't really have to specify the shape in a tuple format. We can just do it like that. Sweet. So our out sigmas sub I would equal the currently generated sigma. And get out of the loop and then return out data and out sigma. All right, now let's try this. So we have train X, train Y. Let's just give these some row names like this, mainly just to use train X, train Y, like we usually do with the dot fit method. So here would be train X equals and train Y equals prep dataset. And this will take train X. We'll keep the S to 5, max sigma to 9, and offset sigma 0.01. And let's do the same thing. And this will be validation. Now, are we doing? How are we doing? We don't see a progress. And okay, this is something you might actually find helpful from TQDM. Import the range. Okay. All right. So uh, uh, I'll show you something. Import TQDM. TQDM is a module that allows you to have progress bars. So TQDM dot. They have T range, which is similar to range, but it will generate a progress bar for that, or it will have what? There is something with GUI or notebook, something for pandas, and what is that one? Decorate an interval. Oh, okay. All right. We might need to do something. I might need to change the our function just to show the progress. Okay, so here we say from TQDM import, what's it called? T range. And inside this, instead of doing this enumerating, Let me just comment that one and let's do it again. For int range images, len of images, and our source image equals this. Now, when we run this, we should have a little progress bar here running and doing all of these nice things. So we can keep track how far are we when preparing the data. Sweet. So now we have train x dot shape should be the same as train x underscore dot shape. Okay, awesome. Now we have train y dot shape should be the same as train y underscore dot shape. Sweet. Now let's see what train y has. These are our sigmas. Now let's check what the maximum is. 9 point something very small, which is our offset, and minimum, minimum. That's basically our offset. So the actual number was like 0.0029 something there, and then we added 0.01 offset there. Maybe this is way too high. Let's do it like that. Actually, we don't actually need to do that. All right, so now we have our data prepared. Actually, let's visualize some of the data first. We need to copy one of the figures and we'll just show some of them. Figure 3, axis 3, and we'll show train at sub 0. And 1 and 2. This 2, 2, 1, 1. What I'm missing something here. Yeah, axis 3, not axis 2. Awesome. These are the images. Now, if we change this train x to train x underscore, this would be our original images. Sweet. So we have the data, we have it right. Now let's get on with our model. So our model would be sequential model, and instead of doing .add modules, we can just say layers equals this, and to keep things a little bit more organized. Okay, so what our first layer would be conv to the something, and this would be and kernels. And what would be the size, kernel size? This would be, say, let's start by 7 by 7, and we'll add activation equals act function, something. Relu should be fast enough here. That's our first layer. Our second layer would be pool. Max, is it pool? 2D, yeah. And pool size would be 2. Oh, our third one can actually copy this block. And then the second one would be, say, 5 by 5. And we'll pool by 2. And we probably will not have enough size to do 3 by 3 and then pool. We'll give it a try. We'll see. By then, now you have a matrix of whatever features got extracted there. So we need to flatten this. So we need to flatten these here, and then we need to add our dense layers. Dense, and this will just take number of units, number of neurons in the multi-layer perceptron. So this would be dense. I don't know, 8 activation equals act function, and our output layer. This will be 1 because this will give us the sigma, and the activation should be all right. Now, if we do model dot summary, we should see something. Okay, the model has not been built yet. Did we build the model? Okay, model build. Sorry. Compiler build. Come on. Something's not right. Input shape. Ah, we haven't put an input layer. Huh. Okay, input layer, and this would be shape equals. We need the size, so we take image train x sub 0 dot shape. What now? Comment. Something is not right. Incompatible with the layer expected. Minimum dimension 4 found 3 dimension full shape is yes, yes, yes. Because our training X, when we prepared the data, we haven't really expanded the dimension. Okay. So to show what happened, train X sub 0, if you get dot shape here, it comes to 28 by 28. Even if you get 0 to 1 like we do before, it's 1, 28, 28. There is a channel missing at the very end here. So our prepared data there, we can expand dimensions here. We have to do all of them again. We expand the dimension, but we did not expand the dimension for. Okay. We need to expand the dimension for these. And now, if we have it in this way, it will not be able, we will not be able to visualize them the same way. Now, if we check what train x dot shape was, so it's 60,000 images, 28 by 28 by one channel, one color, which is grayscale. Now, if we try to do the same visualization here, it should not work. Oh, surprisingly, it did. Okay, I would assume that we have to do it this way. Maybe Matplotlib is much smarter than I thought now. Okay, awesome. Now let's do this one. We getting somewhere. Max pooling. There's something wrong with the max pooling. The last max pooling, it seems. Negative dimension. Okay, yeah, that's what we thought. This by this time, by the time you do 3 by 3, you would have 1 by 1 by 8. So you don't have enough room to do max pooling. Actually, this means we have to comment the 3 by 3 as well. Because 1 by 1 by 8, this is it's like you're condensing the entire image into one value, which is really not fair. So this would be, this will give us 3 by 3 by 8. Okay, and this will be 72. Maybe we need another layer of, so we can take this as 32, then maybe 8. After flatten 72, 32, 8, and then 1. Awesome. Now let's do a quick model.fit. Data, sorry, train X, and what is the other one? Yeah, train Y, and I think validation. Validation. There was a validation data here. Yep. Equals val X and val Y. And we'll set the batch size to say 32. And we set epochs to C10. Something is wrong. You must compile. I haven't compiled the model. Yeah. Model.compile. I believe I will go with Adam. Equals MSE. We are doing regression, so mean square would be good enough. Optimizer. There we go. This error is way high. What would be our mistake here? It is dropping, but it's extremely high. Um, okay, I think I know. First, let's see if it do any better with higher learning rate. Not really. It's just fluctuating around now. Okay. All right. So I think the problem is that the raw data fed into the model is actual numbers. Let's see, train X sub zero and see how does that. Yeah, it's actual pixel intensities, and these range from 0 to 255. This is relatively, and this is a high number. We need to scale down the intensities, which means we need to modify our PEP dataset here and maybe divide this by 255. Now, for the sigmas, we can just leave it as it is. I mean, the maximum sigma is 9, or we can scale it down by 9 and then multiply when we get it back. Let's try it this way first. Something bad happened. Why did that happen? Filtered image. SNS sigma filter image. This one and filter. It says here that we have an extra dimension somewhere in the source image. Ah, see, this was that mistake. This should be underscore. We've been doing it wrong the whole time. Wow. Basically, we were taking train X, modifying to this one, and then when we run this again, we take the same train X and do it here. So yeah. Okay. All right. We are. Oh. Oh yeah. When you show the images, you might need to multiply by 255 again. No. There's something wrong here. It's all zeros. I have a feeling that this zeros-like thing is kind of doing something. G-type equals float. I think when we're dividing by 255 here, it's kind of doing truncation. Um, it's not giving, it's jamming floating point numbers into integer variables. There we go. See, this is why I actually wanted to do this live, mainly just to run into these kind of problems. Awesome. And then let's do this one, and let's do that one and see what happens. Okay. All right. Decent error, dropping fairly fast. Mm, it is still way high, though. Now the arrow started dancing around up and down. This means that the learning rate is higher than it should. Terminate that and do it again. Yep. Oh, actually, that's misleading because we continued on the same model before. We need to run this and build it and compile it again to get the training from the start. This error is really, really high. It dropped significantly, yes, but still considered relatively high. I think we might need to scale down the sigmas and then multiply by the, let's do max sigma equals 9. And here we'll do max sigma equals max sigma. We need this variable later on when we decode the output of the network. When I put like a period after a number, this means forcing it into being float. It's like 9.0, but without the zero. Same here. And we can probably remove this one. How are we doing here? Not good, not good. Okay, let's give it a fresh running from the start. The reason this is blank is that it is actually doing data processing here. Now it's doing the training. This error is now missing because you have to multiply it by 9. 9 squared actually multiplied by 81. So if it's 0.041, multiply this by 81. This is our actual error. It's just we are scaling it down this way to keep the gradient very kind of contained when it's training. Mm, we need also to take square root of that. It's about 1.5 off in terms of sigma estimation. Hey, cool, not bad. 10188. We are down to 1.23 difference from the sigma estimated sigma. No, it's increased again. More, it might be a little bit overfitting here. No, validation is a little bit high. Not alarming, it's higher than the loss, which is understandable, but it's not at an alarming rate. When you find this, the training loss dropping, but the validation loss increasing, this is when you really get worried because this means the model is memorizing the training data and it is failing to generalize on the validation data. Another factor we haven't considered is that we are using a relatively small model. There is nothing much we can do in terms of number of layers. Maybe we can drop everything to 3 by 3 or something. So if we make this 3 by 3, 3 by 3, then we can maybe repeat this several times and maybe exclude a couple of pooling. But another thing that we also have here is number of kernels only 8. It's relatively small number of kernels there. The error is dropping. It's actually interesting to see that. I didn't expect it would work like this from the first time, but we'll see. 149. We're almost to 1 sigma off. Okay. Okay, it's done. What we can do before I take a break would be let's test the model. Let's run a couple of images through it and get the sigmas, scale them back to whatever max sigma was, which was, I don't know, what was the max sigma? It was 9. So we'll divide by max sigma, and then we will unfilter an image and see what it looks like. Okay, so let's take our model dot predict. The autocomplete is failing on me. And we'll give it validation x sub 0 to 1 to maintain the shape. And let's see what that gives us 0.73 sigma. Now let's see what the actual value was, validation y sub 0 to 1. 0.93. So it's not that bad. We're not that off of this. Okay. So let's call this predicted sigma, and let's divide by max sigma. This should give us, oh, we need to paint that. And instead of having this thing, we need to make these verbose equals 0. We are not dividing, we're multiplying. Okay. Now let's see what the val y. We haven't divided now. Val y sub 0 to 1 multiplied by max sigma. So 6.58 as compared to 8.36. It's not trained properly yet, but we can just test that. So let's make our filter. Gaussian filter. And what was the shape? What was the shape that we started with? What was the default shape? Fine. Okay. See, this is what happens when you don't use variables. So filt size equals 5. And then S should equal filt size. Same here, S should equal filt size. And we are not going to run this now because now we will change our data and we don't want that. So filter size is, we'll say shape equals filt size. I haven't actually run it. Did I put the right name up there? Not here, not here, not there. Fill size, okay. Fill size equals 5, and then this would be fill size and fill size. What else do we have here? Sigma predicted. So, okay, so let's see what fill looks like. Oh, predicted sigma is not. Oh, okay, now this starts to be annoying. Predicted. This is our filter, really? No. The shape of the predicted is not the same. Predicted. Okay, let's. Let's see what predicted sigma looks like. It's an element in a 2D array. It's a 2D array that is 1, 1, 1, and 1. So if we check shape, it will be 1 and 1. So we need these values out. I think there is something called item. Yes. We can just say dot item here. That's it. All right, this is our filter. Now let's unfilter an image. Okay, let's take sample equals this val x, and predicted sigma would be this one. Let's remove that filter size here for just a second. We'll remove that as well. Now we want image. Let's call it source equals sample sub 0, this, and 0. This is okay. So this 0 gets rid of the batch size dimension. These are the 28 by 28, and this gets rid of the channel because we don't need it. Now, this is our source image. Not source, actually, blurred image. Because our source image equals val x underscore 0. And then unblurred image equals sample equals unfilter image. What do we have here? We'll give it the blurred image and our filter. I have no idea if this would work at all, but let's just wing it. So make a figure will show the source, the blurred, and the unblurred. Let's put this as n. This would be n and n plus 1, and this would be n. Now x is figure 4. X is 4. We'll take 3, and then we'll get here the source image. Should be ready. And this would be 4. This would be the blurred image. And this would be 4. And this would be the unblurred image. And this would be 4. Source blurred unblurred. Here goes nothing. I have honestly I don't know if it will work. I'm not sure even that if the model got trained properly. There was one full sigma difference there. Oh, we have bigger problems. N equals say 1. Hey, hey! Well, It did actually kind of work. Okay, let's try image 100. Sweet. Mm, and 50. Okay, so there are some kinks here that are not really um, perfected yet. My assumption is that the model is not fully trained yet, so we might actually give it another go to let it work itself around a better estimation. Let me just add one last thing. I wanted to add what the estimated sigma is and what the correct sigma was. So I believe figure 4. So title is this. Yes, awesome. So we'll do here an f string and we'll take two things here. Predicted sigma equals and original, uh, let's just call it true sigma. And let's get the true sigma. Where's it gone? True sigma would would be val y sub val val y sub n. Not sure this is correct. In terms of formatting, I mean. Ooh. Okay, these decimal points are very, very large. We need to format this a little bit. So we'll do it 0 point or maybe 1.3 float. Actually, yeah, it's supposed to be 4.3 float. So we need 3 decimal points, and we have to count the periods. This is 4, so this should be 5.3. 5.3 f. Yep. Okay, so for number 6, for number 50, image number 50, it wasn't working that well. Let's see one of the ones that worked nicely, like 1. The true sigma's way. Yeah. The true sigma was not, where did that go? Was not scaled up by max sigma. Still relatively high. I think most of the errors that were now something is not adding up here. We do clipping for the negative values. There would be negative values when you do unfiltering, and we do the clipping with that. But I am not sure if this is correct. This is kind of close. Also, the results look too good to be true, to be honest. It seems like it's identical somehow. Mhm. It's as if I'm plotting the wrong image. Unblurred image, unfiltered image, blurred image and filter. Blurred image text from sample and filtered is with predicted sigma. Mm, maybe it is good, I don't know. Oh yeah, this one was bad anyway, so yeah, it's trying to do it, but it didn't work in this case. Okay, now let's run the model a little bit longer. Let's give it 5 more iterations. Hmm, it's oscillating here. It's not really doing much. I'm just hoping the momentum for Adam would pick up eventually. Yeah, it's going up again. Now this is going down and this is going up. This is a sign of overfitting. Oh, yeah, okay, drop down again. It is finding a way. All right, let's do that again. No, still messing up very badly. Another thing that's really bugging me is that the true sigma is way off, or the predicted sigma here. And yet this is actually looking good. I want to see what this is. If it's too good to be true, it usually is too good to be true. Mm, Okay, let's give it 5 more epochs. One thing I don't like about Jupyter notebooks is that you can run each cell independently. So sometimes you have something that you changed in the memory. I can't remember what it is, but it is kind of there and can give you some misleading results. I'm worried this is one of them. You know what? I want to test what the blurred image, what the unblurred image and source image. Uh, what's the difference between them? I can just subtract them and then maybe do a sum. I mean square. You notice here when we start when we start the trainer again, because we do compile again here, so this is the new optimizer. Starts with a higher momentum. That's why it overshoots and then tries to drop down. You might actually want to put this in a different cell. Okay, let's do this. I still don't like that. And let's see what source image and unblurred image. Source image minus unblurred image. We square that and dot sum. Oh, dot me. My goodness, div is actually an error. I don't know where it is. I can see it with my naked eyes. Maybe I'm plotting the wrong image here. Let's see what show image has. I'm worried that may be referring to some global variable. So image takes image, CMap, title, set visible, and nothing. Filter image takes image, image, image F, filt, filt F, image F times filt F, image fill, image F, filt F, filt, and then image F divided by filt F. It is working there. Let me see one more thing. Source image. Okay. Now unblur the image. Oh, okay. So the source image is coming from this one, and this one was not scaled. That is why. Now, let's see source image. I'm so happy I did this video this way. There is a lot of tricks. Okay, so they are close. Now let's see what the other image says, which was, what was it? 50? Yeah, this was the bad one. Well, it has higher error. That you can still actually recognize the 6. Okay, so this is another thing. There is a difference between the error and the utility um, between samples or images. For example, the image might look bad, but it might still be useful. To actually test that, you can get a pre-trained model that can recognize these digits and then make it recognize the unblurred image and see if it can actually recognize it correctly. Okay, so we'll give it a long run. We'll take a break now and let's give it like, say, I don't know, 50 episodes, 50, sorry, epochs here. And we'll start from scratch, let it do the whole thing from scratch, and then we'll come back. I will leave the video. I will just speed it up in the editing later on. All right, we're up to epoch 47, 48. I don't like how the arrow is working here. Looks like stagnating. Oh, I used 0.0001 for the atom. Okay, this might be a problem. Hmm. We might need to increase number of filters. That's the last epoch. Okay, well, I got the 6 right. Still a little bit blurred though, but better than before. Now, how about the other ones? We got the 3 right, and now you can see the sigmas are actually getting closer. Much better than before. Some of them are not really that good. Although the sigma is kind of close. I want to try something. I have a bad feeling about this, but it is something that's worth trying. We'll take images, we'll filter them. I think we already did that before. Um, okay, I want to try this with a new filter. Would be the same exact value, but a new one. Okay, now how about 1.1? How about 0.9? Okay, let's try the same thing. Not this one. We want this one. But on the numbers, we don't need that. Image color, filter, 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 filter to unfiltered, and we will plot these. Now, instead of this, I want to take the source here, val x underscore n. This is how it should look like. This is not right. If we get the sigma right, it should look like that. Now let's see what happens if I put 1.1, 1.2. Okay, okay. Now what happens if it was 2? And if it was 0.82? Okay, this was mainly just a sanity check to see what's the effect of changing the error between the predicted sigma and the true sigma. But it looks like things are working fine. Some of them, oh yeah, you can actually see the difference here. You can see the shades in the background here, which were not filtered properly because the sigma was not correct. Okay, alrighty. So there you have it. It's not bad. It actually works. Now, one thing we can also try is increasing the model size. So we can maybe make this 16, but then remember that with the model that we have, in many cases we can find the training loss is dropping, but the validation loss is increasing. So this is an alarming sign. We let it run anyway, but in case it's not actually training or it is overfitting because now we have so many parameters with a number of kernels, and this goes here, here, and this flatten might need to change as well. Because of this, now we have so many parameters might memorize the data and will fail to generalize. If this happens, we'll see we can add dropout layers to mitigate that. So let's actually try this one. And now we have 144, 32, something. That's okay. That's all right. We'll keep the same learning. Actually, we can increase the learning rate. We change the model anyway. And let's do that. Yeah, sorry to increase here again. Okay, to combat that, we will need to add some dropout layers. So we can add dropout and give it, say, 0.25, and maybe another dropout here with another 25. Although it is dropping here. Okay, let's terminate that. And let's redefine the model again. You notice that there here is much higher. This is due to the dropout layers, which are causing the training to look like it's not the, it's causing a struggle for the training module. But then this will reflect very good on the validation. You'll find the validation dropping much faster because it had seen more variations and more neurons got engaged. So when some neurons gets zeroed with dropout 25 and dropout 25, this causes like 25% of the neurons or the feature maps connected to these neurons to be zeros, then the other neurons have to actually work. It's starting to stagnate here. Oh, nice. All right, I think I'm gonna leave this one running, take another break, and then when I come back, we'll talk about how to use the callbacks to just do some live plotting when doing that. So you can do that to say plot a sample, take a sample of the data set and plot it this way. Um, every batch, which is every step here, or every epoch, which is every line after each epoch. Then we can take few samples and maybe plot them. Sweet. So I'll take a break now. This part I will speed it over in the editing. I'll see you in few edits. Okay, let's see how this one did. Not bad, not bad, not bad. Really, really nice. That's actually and the image 50, which was terrible, is now actually very good. Image 3 is my image 5000 is also very good. So awesome. That's all done now. So there you have it. Deep learning by doing a regression model over the sigmas of the filter. Now, one last thing I just wanted to show you is adding callbacks. Okay, so a callback is a function that will be called at different events with the fitting. You can actually check the different callbacks. If we go to Keras, must be recording. I am awesome. Keras callbacks. So here, you can use it in the fit loop. You can say model.fit, put your data set, epochs, whatever, all the other parameters, and then callbacks will be a list, different callbacks that you can have here. There are different types of callbacks. One of them is early stopping, when to stop. Basically, if the error gets increasing, so it's error is not enhancing, it's not dropping further. There is model checkpoints, saving the last or the best model, and you can give it the whatever path name here. And this is essentially an F string that you will get. You can use epoch and validation loss and all other parameters to put it in the file name. One of the cool callbacks as well is the tensor board, which is a tool by Google to actually visualize the um, training progress. Now, there are other callbacks, like say reduce on plateau. So when the error keeps steady or just increasing and decreasing again, so it's not really enhancing, then maybe you can drop the learning rate, reduced learning rate on plateau. There is learning rate scheduler, and this one you can set steps like you can have this function for scheduler here. Like first 10 epochs, we'll use the same learning rate that we have. After that, we will use the learning rate multiplied by whatever discounting factor. This can be very, very useful in complicated models. GANs can make use of this. There is also remote monitor. I believe this would open a socket that you can publish on, so you can grab your data from another server, another machine. There is also Lambda callback, my favorite. This allows you to create a custom callback that you can use there. Terminate on nans, that's also another good one. Basically, what it does, when it sees nans anywhere, it will just terminate the training. CSV logger and progress bar logger, this is mainly to dump some data into CSV file. Mainly, I think, training stats. And progress bar logger is, as the name says, it's a progress bar. So let's just say take the lambda callback here and let's do something with it. Which one were we? Let's just close these. Okay, so the way we add is callbacks equals something. Let's call it my callback. There is also base callback, which is if you want to really make a fully fledged callback for callback class, then you can inherit from the base callback, and then you have different functions on training and on training starts, on batch change, and so on and so forth. Okay, so where was I? Was that the one? Yep. Okay, so we'll use my callback, and then my callback equals lambda callback. And here you can specify different functions or different functions of callables that you can call on each one of these. And we will be using on epoch begin, sorry, on epoch ends. To visualize the performance of the last um, of the model after the last epoch. Okay, so what we want is to plot something like, say, this. So let's copy that. Actually, let's copy all of that here, and we'll put it in a function. Show results callback. Let's call it my show results callback. And let's just add this here. Okay, so we need some parameters here to pass in. First of all are the figure and axis. You can have these outside, say here, and we'll call them fig and axis. Fig, axis. And then we will use axis like this, and we'll use fig like that, and whatever that is here. Let's leave this as none for now. We'll see how to call this. Okay, and this would be the sample number. Now we need the samples. So we'll call them val x and val y, and we'll also pass the val x underscore. And then n will be numpy.random.rand int between 0 and the length of val x. So 0 and len of val x. Okay, so this will give us a random sample index. This will give us the actual sample, true sigma, predicted sigma, so on, so on, so on. Now, one last thing, something I'm missing here. Oh yeah, this rand int can give you the last element. So the last element you cannot actually have n+1. So, oh, actually you can, because this is not inclusive. Okay, it should work. Cool. Now, what we want, we will make up the figure first, and then let's make it on callback start. I did something wrong. Move to another one. Begin. On epoch begin. Now, we want to call this function and pass all these arguments there. On epoch begins, we'll take two parameters, which are the epoch number and the logs, which is a dictionary. So we can add this here and logs, but if we do it this way, then this function is really very, very tailored to that, and we don't want to do it this way. What we can do is to add a lambda function here, and we'll take an epoch n and logs, and with that we will call our function my show results callback here. This is getting very, very messy. It's just okay, and we'll open that. We'll give it fig4, x is 4, because we take figure axis, and then we need val x underscore, and val y. Val x underscore, and val y. We can drop these here, and this should work, hopefully. Let's see. It is working. It's not crashing, but it's not showing anything. Yes. There is one thing I missed here, which is fig.canvas something. Dot canvas something. What's it called? I forgot what it was. Not here. Perhaps here. One of these. No. I always forget that one. Fig canvas something. Dot. Basically, it's a command that flushes the changes to the figure. There it is. And let's go here. And there we go. Now let's see if that works. Okay. On epoch begins, it did the very first image. And then when the epoch ends, it will sample another image and show you how it looks. Okay, come on. Beautiful. Now you can also do this at a batch level. But will be much, much slower. Because every batch is basically every step. Every equal sign here is a step and represents one batch. So it will be much, much slower because plotting and showing images is fairly slow. So there we go. Now you can see why it looks very, very slow now. Barely at the 35th, 36th batch with that. Now, if you show this from the start, it will look actually, it will show you how the progress looks like here. So let's do this, and this. That's not funny. I rushed it. I rushed it so quickly. Okay, my bad. We'll start over. It's now preparing the data, and filter size. Okay, now we don't need this filter size technique, and we don't need it here either. And something crashed. What happened? Well, something filter this, filter that. What does it say here? Division by 0. Okay. It gave zeros, really? Maybe the network was very, very bad at the start. I don't know. Yeah, that's another thing you can see. Um, when the network starts training, it will be chaotic. So it will give you very bad values. Some of them may be zeros, and you will be dividing by 0 at some point. You can capture that with a try and catch, and maybe skip it. So yeah, this is how you can incorporate a callback function into your training. There are so many other callbacks that you can play with, so have fun with them. This pipe is terrible. Okay, so this code will be uploaded on Moodle, so please have a look at it. I really wanted to do this as a live coding session, mainly just to see all the other problems we had to go through. It's one thing to have the code ready and running. You can just run it and just see it working. And it's another thing to see it actually being written step by step. Hope you enjoyed that and have fun. Okay, I'll just stop that now.